In this video, we're going to talk about organic chemistry. Now, this video is for those of you who are taking the first semester of organic chemistry in college. Organic chemistry focuses on organic compounds, compounds that contain carbon atoms. Now, carbon likes to form 4 bonds, but you also need to know the number of bonds that the other elements like to form. So elements in the first group of the periodic table, like hydrogen, they like to form 1 bond. Beryllium, for example, likes to form 2 bonds. Boron, which has 3 valence electrons, it likes to form 3 bonds. Carbon has 4 valence electrons. Carbon likes to form 4 bonds. Nitrogen likes to form 3 bonds in organic chemistry. Oxygen likes to form 2. And elements like fluorine and the other halogens, chlorine, bromine, iodine, they like to form 1 bond. Now, there are cases where chlorine, bromine, and iodine can form 7 bonds. But we're really not going to cover that in this video. I do have another video entitled Lewis Structures, which goes into that detail for those of you who might be curious. Now, understanding this is important because it helps us to draw Lewis structures. So for instance, let's say if we want to draw the Lewis structure of water, H2O. Knowing that oxygen likes to form 2 bonds and hydrogen likes to form 1, we can start with a structure that looks like this. Now, oxygen likes to have 8 electrons. Each bond represents 2 electrons. So that's a total of 4. To get to 8, we need to add 2 lone pairs. So that is the Lewis structure for water. Now, the bond between hydrogen and oxygen is known as an H bond, or a hydrogen bond, which is a special type of covalent bond. Hydrogen bonds occur whenever H is directly attached to nitrogen, oxygen, or fluorine. Hydrogen bonding explains why water has such a high boiling point. Now, let's say if we have methyl fluoride. How can we draw the Lewis structure for that molecule? So we know that carbon likes to form 4 bonds, so we're going to put that in the middle. Hydrogen likes to form 1 bond. Fluorine also likes to form 1 bond, so this is the best Lewis structure that we can make. And if you want, you can add 3 lone pairs to fluorine so that it has 8 electrons around it. Elements in the second row, like carbon, nitrogen, oxygen, and fluorine, they like to have 8 electrons. They don't always have to have 8, but ideally speaking, they like to have 8 so that they can be stable. But that's the structure of methyl fluoride. Now, the carbon-fluorine bond is a polar bond. Carbon has an electronegativity value of 2.5, and the electronegativity value of fluorine is 4.0. Whenever the electronegativity difference between 2 elements is 0.5 or more, the bond is said to be polar. So this is a polar bond. It's not a hydrogen bond because fluorine is not directly attached to hydrogen, but it's a polar covalent bond. Now you might be wondering, what does it mean for a bond to be polar? A polarized object is an object that is neutral overall, but has charge separation. That is, one side is positive and the other side is negative. So this is a polarized object. The bond is polar because fluorine carries a partial negative charge due to the fact that it's more electronegative than carbon, so it pulls electrons toward itself. And carbon, being less electronegative, has a partial positive charge. So due to that charge separation, we can say that the carbon-fluorine bond is polar. Now the carbon-hydrogen bond, that's a non-polar bond. The reason being is the electronegativity difference between carbon and hydrogen is less than 0.5. Carbon, we said its electronegativity value is 2.5. Hydrogen is 2.1. So the difference between the two is 0.4. So understand this, anytime you see a hydrocarbon or a bond that contains carbon and hydrogen, those bonds are nonpolar bonds. Because sometimes you need to determine if a molecule is polar or nonpolar. So, for instance, methane, CH4, that's a nonpolar molecule because it only contains carbon and hydrogen. So far, we've considered two types of covalent bonds: polar covalent bonds and another special type, which are hydrogen bonds. And we also talked about nonpolar covalent bonds, like the carbon-hydrogen bond. That's a nonpolar covalent bond. But you need to understand the difference between a covalent bond and an ionic bond. In a covalent bond, the electrons are being shared. They can be shared equally or unequally. So in the case of the hydrogen molecule, H2, the electrons in this bond are being shared equally between these two atoms because the atoms are identical. So that's known as a nonpolar covalent bond, which I'll put CB for covalent bond. In the case of hydrogen fluoride, that is a polar covalent bond. Hydrogen has an electronegativity of 2.1. Fluorine has a value of 4.0. So hydrogen is going to be partially positive. Fluorine will be partially negative. And this is a special type of polar covalent bond. That's a hydrogen bond. So those are two examples of covalent bond. You have nonpolar covalent bonds and polar covalent bonds. So make sure you understand the difference here. The electrons are shared equally. That's the key word. And in this case, the electrons are shared unequally. Fluorine is going to have a tighter hold on those electrons. Now let's talk about ionic bonds. So in an ionic bond, the electrons are not shared, they're transferred. A good example is the reaction between sodium metal and chlorine. Sodium has 1 valence electron. Chlorine has 7. Sodium is a metal and chlorine is a nonmetal. Metals like to give away their electrons because they're electropositive. Nonmetals like to accept or acquire electrons because they're electronegative. So sodium is going to give 1 electron to chlorine. A half arrow represents the flow of 1 electron. A full arrow represents the flow of 2 electrons. So in this reaction, sodium is going to turn into the sodium plus ion, which is known as a cation. Positively charged ions are called cations. Now chlorine, when it acquires an electron, it becomes chloride. So now it has 8 electrons. It's going to now have a negative charge. Negatively charged ions are known as anions. Now going back to physics, you know that opposite charges attract one another. So a positively charged ion will feel a force of attraction to a negatively charged ion. So these two charges, they're attracted to each other. And that force of attraction, that electrostatic force, is what keeps the ions in an ionic crystal together. So that creates that ionic bond, that electrostatic force of attraction that pulls the sodium and the chloride ions together. So now you know the difference between an ionic bond and a covalent bond. So now we're going to spend some time drawing Lewis structures of certain organic compounds. But before we do, let's talk about some common names of alkanes. Alkanes are saturated organic compounds, meaning that the carbon atoms are filled with hydrogen atoms. Methane is a 1-carbon alkane. It's methane. A 2-carbon alkane, C2H6, this is known as ethane. C3H8, this is called propane. C4H10, this is known as butane. So alkanes generally follow this formula, CnH2n plus 2. So a 5-carbon alkane will have 12 hydrogen atoms. If N is 5, then it's going to be H, 2 times 5 plus 2. So that's 10 plus 2, you get 12. A 5-carbon alkane is known as pentane. A 6-carbon alkane is known as hexane. You may want to take some notes, by the way, because you'll need to know this at least up to 10. The 7-carbon alkane, that's heptane. Next, we have octane. And then after that, that's a 20. This is nonane, or if you want to call it nonane. And then C10H22, that's known as decane. Now let's talk about how to draw the Lewis structure of C2H6. C2H6, we know that's ethane, and you can write the condensed structure like this. It's CH3, CH3. So this tells you how many hydrogen atoms are on each carbon. First carbon has 3 hydrogen atoms, and that's attached to the second carbon, which also has 3 hydrogen atoms. So that's how you can draw the Lewis structure of ethane. Now what about C2H4? How would you draw the Lewis structure for that? So this time, each carbon atom is going to have 2 hydrogen atoms instead of 3. Because it's a total of 4, and you want to make sure that the 4 hydrogen atoms are distributed equally. So what bond do we need between the 2 carbon atoms? Well, we know that carbon likes to form 4 bonds. So the only way this is going to happen is if we put a double bond between the 2 carbon atoms. And so this is known as an alkene. Alkenes contain at least 1 double bond. Alkanes do not contain double bonds. So a 2-carbon alkene is known as ethene. Now what about this one, C2H2? How can we draw the Lewis structure for that? Well, we have a total of 2 hydrogen atoms. So we're going to put 1 hydrogen atom on each carbon. And in order for the 2 carbon atoms to have 4 bonds, we need to put a triple bond in the middle, because carbon likes to form 4 bonds. And so whenever you have a hydrocarbon with a triple bond, you now have what is known as an alkyne. A 2-carbon alkyne is known as ethyne. The common name for this is acetylene. And the common name for this compound is known as ethylene. Alkenes and alkynes are known as unsaturated compounds because they don't contain the maximum number of hydrogen atoms per carbon atom. Alkanes are known as saturated compounds. So make sure you keep this in mind. Now let's focus on the carbon-carbon bonds. What would you say, which of these bonds is the longest bond? The carbon-carbon single bond, the double bond, or the carbon-carbon triple bond? Which one is the longest and which one is the shortest? You need to know that the carbon-carbon single bond is longer than the carbon-carbon double bond, and that's longer than the carbon-carbon triple bond. The length of the carbon-carbon single bond is 154 picometers, which is 1.54 angstroms. 1 angstrom is 100 picometers. The CC double bond is 133 picometers in ethene, and in ethyne, it's 120. So what you need to understand is that triple bonds are short bonds, whereas single bonds are long bonds. Because sometimes you may get a test question that asks you something about bond length. Which of these bonds is the shortest, or which of these bonds is the longest? So single bonds are longer than triple bonds. Keep that in mind. So now that we've talked about bond length, let's talk about bond strength. Which bond is the strongest? The single bond, the double bond, or the triple bond? What would you say? The single bond is the weakest. The triple bond is the strongest. Why is that? Well, it's easier to break one bond instead of 3 bonds. Imagine trying to break a pencil. It's easier breaking one pencil than trying to break 3 pencils at a time. 3 bonds are stronger than 1. Now let's talk about sigma and pi bonds. A single bond contains 1 sigma bond. All single bonds are sigma bonds. A double bond contains 1 sigma and 1 pi bond. The triple bond contains 1 sigma and 2 pi bonds. Now, which bond is stronger, a sigma bond or a pi bond? You need to know that sigma bonds are stronger than pi bonds. So it's harder to break this bond versus just one of the pi bonds in the triple bond. Not all 3 bonds, but one of the pi bonds. So in summary, a triple bond is stronger than a single bond because you're comparing 3 bonds to 1. However, a sigma bond is stronger than a pi bond when you're comparing 1 bond with 1 bond. So I'm just going to say that one more time. Sigma bonds are stronger than pi bonds, but triple bonds are stronger than single bonds. Now the next thing we're going to talk about is bond order. What is the bond order for a single bond, a double bond, and a triple bond? This one is pretty straightforward. For a single bond, the bond order is 1. For a double bond, the bond order is 2. And for a triple bond, the bond order is 3. So that's just something to know. Now let's talk about hybridization. What is the hybridization of the carbon atoms highlighted in green? Would you say it's S, sp2, sp3, sp, dsp3, d2sp3? What would you say? A quick and simple way to determine the hybridization around a certain carbon atom is to count the number of atoms attached to that particular carbon atom and the number of lone pairs that it has. So this particular carbon atom is attached to 4 other atoms. So you could think of it as having 4 groups around it. So the hybridization is going to be S1P3 because the exponents add up to 4. Now let's say if we want to determine the hybridization of this carbon atom. That carbon is attached to 3 other atoms. So it has 3 groups around it. The hybridization is going to be S1P2 or sp2 hybridized. And then for this particular alkyne, the carbon atom has 2 atoms attached to it. So for 2 groups, it's going to be sp hybridized. So that's a quick and simple way to determine the hybridization of a carbon atom. Here's a question for you. So let's say we have a Lewis structure that looks like this. What is the hybridization of not the atoms, but the bond? What is the hybridization of the CH bond and also of this particular CH bond? What would you say? If you were to get a test question that asks you that question, how would you determine the hybridizations of this bond highlighted in red and this bond highlighted in blue. What you need to do is determine the hybridization of the atoms that are connected to those bonds. So what is the hybridization of this carbon atom? That carbon is attached to 4 other atoms. So it has 4 groups, and so it's going to be sp3 hybridized. Now you need to look at the other atom, the hydrogen. Hydrogen is only attached to 1 atom. So what do you think the hybridization of hydrogen is going to be? This is going to be S. So thus, the hybridization of the CH bond, that's going to be sp3-S. You simply just write both of these together. Now what about the CH bond highlighted in blue? What is the hybridization of that CH bond? Feel free to pause the video if you want to try it. So let's start with the carbon atom. That carbon is attached to 2 other atoms, so it's going to be sp hybridized, and hydrogen is always S hybridized. So that particular CH bond is going to be sp-S hybridized. Now another question that you might be asked, given this compound, is how many sigma and pi bonds are in this compound? Feel free to pause the video and try it. So first, let's count the number of sigma bonds. Every single bond is a sigma bond. So we have 1, 2, 3, 4, 5, and there's 1 sigma bond in the triple bond. So we have a total of 6 sigma bonds. Now, how many pi bonds do we have? We know that a double bond contains 1 pi bond. A triple bond contains 2 pi bonds. So this molecule has 6 sigma bonds and 2 pi bonds. So that's how you could determine the number of sigma and pi bonds in an organic compound. Now the next topic of discussion is how to calculate the formal charge of an element. So let's use carbon as an example. Calculate the formal charge of each carbon atom for these 3 situations. If you know how to do it, feel free to go ahead and try it. Now there's a formula that will help you to calculate the formal charge of an atom. And here it is. The formal charge is going to be equal to the number of valence electrons of the element minus the number of bonds and dots attached to that element. So for the first example, carbon has 4 bonds. Let me say it again. Carbon has 4 valence electrons. It's in group 4A of the periodic table. And in this example, it has 3 bonds, 1, 2, 3, and it doesn't have any dots around it. So 4 minus 3 is 1. So this particular carbon atom has a formal charge of +1. So we could say that it has a positive formal charge. Now moving on to the next one, it's going to be 4 valence electrons minus 3 bonds and 1 dot. So we got 3 bonds, 1 dot. That's 4 minus 4, so that's 0. So this one is neutral. It doesn't have a charge. Now for the last example on the right, the valence electrons of carbon will still be the same. We still have 3 bonds, but this time we have 2 dots. 1 lone pair is equivalent to 2 dots. So 3 plus 2 is 5. 4 minus 5 is -1. So this particular carbon atom has a negative charge. We said that We said that positively charged ions are called cations, and negatively charged ions are known as anion. When you add a carbon to it, this is called a carbocation, and on the right, this is called a carbanion. Carbanions have negative charges. Now, when you have an odd number of electrons, you have what is known as a radical. So a 1-carbon radical is known as a methyl radical. Radicals tend to be neutral. Now let's work on some more examples. And go ahead and calculate the formal charge of the sulfur atom, and also calculate the formal charge of the nitrogen atom. Go ahead and take a minute to work on that example, or those two examples rather. By the way, for those of you who are looking for a specific topic, but for some reason you're not finding it in this video, when you get a chance, do a YouTube search. Type in organic chemistry playlists. I have two playlists, an older one and a newer one. The newer one is going to be more helpful. So in that playlist, chances are you could find a topic that you might be looking for. So just feel free to take a look at that as well. I'll be posting some links in the description section below of this video with some other topics that might help you with the first exam that you might be taking in organic chemistry. So feel free to check that out as well. So let's begin. Let's start with sulfur. Let's write the formula. So the formal charge is going to be the number of valence electrons minus the sum of the bonds and dots around that element. Now, how many valence electrons does sulfur have? Sulfur is found in group 6A of the periodic table. If you don't have one, you could do a Google search. You could find it in Google Images, and then you could pull up the periodic table. If you look for sulfur, it's right under oxygen, and it's in group 6A, which means that sulfur has 6 valence electrons. In this structure, it only has one bond attached to it. Now, how many dots does it have? Well, we have 3 lone pairs, which is equivalent to 6 dots. So this is 6 minus 7. So the sulfur atom has a -1 formal charge. Now, for nitrogen in the ammonium ion, nitrogen has 5 valence electrons. It's in group 5A of the periodic table. In this structure, it has 4 bonds, no dots. So 5 minus 4 is 1. So this particular nitrogen atom has a +1, or some may say a 1+ formal charge. So that's how you could determine the formal charge of an element. Now let's go back to this structure, because there's another question that I'm going to ask that teaches another concept. How many bonding electrons and non-bonding electrons are present in this ion? What would you say? A lone pair represents a pair of non-bonding electrons because they're only attached to one atom, so they're non-bonding electrons. In a bond, you have 2 bonding electrons. So to count the number of bonding electrons, this is going to be 2, 4, 6, 8. So this particular ion has a total of 8 bonding electrons because it has 4 bonds. Each bond contains 2 bonding electrons. Now, how many non-bonding electrons do we have? 2, 4, 6. There's a total of 6 non-bonding electrons, which equates to 3 lone pairs. So make sure you understand that concept. One lone pair is equal to 2 non-bonding electrons, and one bond equates to 2 bonding electrons. Now let's continue our discussion of drawing the Lewis structures of organic compounds, as well as considering the functional groups of those compounds. So let's consider CH3, CH2OH, and let's compare that with CH3, CHO. So feel free to pause the video and go ahead and draw the two Lewis structures. So for the one on the left, we have a carbon that is connected to 3 hydrogen atoms, and then it's attached to a CH2 that is a carbon with 2 hydrogen atoms, and that's connected to an OH group. Keep in mind, oxygen likes to have 2 bonds, and it's going to have 2 lone pairs. So that's the Lewis structure for this molecule. Now, whenever you see an OH group, this is the functional group of an alcohol. And the fact that we have 2 carbons, this is associated with the alkane ethane, but because we have an alcohol, we can name it ethanol. So alcohols have the suffix OL. So this is ethanol. Now what about the structure on the right? So we have a methyl group that is a CH3, and that is attached to a carbon atom. Now it's CHO instead of OH. When you see CHO, this is the functional group of an aldehyde. If we were to write OH, this is not going to work because carbon doesn't have 4 bonds. So that tells you that we need a different structure. An aldehyde contains a carbonyl group, which is basically a carbon double bonded to an oxygen. And then here's the hydrogen. So in this case, every carbon atom has 4 bonds, every hydrogen atom has 1 bond, and the oxygen atom has 2 bonds, which is what they usually have in neutral molecules. And of course, the oxygen is going to have 2 lone pairs, as it did here. So this is a carbonyl, and this particular carbonyl, which is attached to a hydrogen, that is known as an aldehyde. So that's the name of the functional group. A 2-carbon aldehyde is called ethanol instead of ethanol. So it ends in AL as opposed to OL. The common name for this aldehyde is acetaldehyde. Now let's consider these 2 examples, CH3OCH3 and CH3COCH3. Notice the difference. So go ahead and draw the Lewis structure for these 2 organic compounds. For the first one, we have a methyl group. That's a carbon with 3 hydrogen atoms. And then we have an oxygen in the middle. As we said before, oxygen likes to form 2 bonds, and then another methyl group to the right of that. So this particular compound has a functional group known as an ether. An ether is basically an oxygen atom between 2 carbon atoms. That's an ether. Now, because this particular ether has 2 methyl groups, one to the left, one to the right, this is known as a dimethyl ether. The prefix di means 2. Tri means 3. Tetra means 4. Penta means 5. Now, how would you draw the Lewis structure for the compound on the right? So we know that we have a methyl group on the left, and then there's a carbon atom. Now, where do we put the oxygen atom? If we put it in the middle, this carbon atom is going to have 2 bonds. So to fix that problem, we need to put it up here. We need to make another carbonyl functional group, and then write the methyl group. So in this case, every carbon atom has 4 bonds, the oxygen atom has 2 bonds, and every hydrogen atom has 1 bond. That's why it's important to know the number of bonds each element like to make, because it makes drawing the Lewis structures a lot easier. Now, even though we have a carbonyl functional group, the name of the functional group for this particular molecule is different than an aldehyde. This is known as a ketone. When the carbonyl group is in the middle of the chain, it's a ketone. When it's at the end of a chain, it's an aldehyde. So to name this particular ketone, it's called propanone. Think of propane for a 3-carbon alkane. So a 3-carbon ketone is going to be propanone. ketones have the suffix -one. So notice the difference between a ketone and an aldehyde. A ketone will have the carbonyl group in the middle. An aldehyde will have the carbonyl group at the end. So an aldehyde has a hydrogen that's attached to the carbonyl group. A ketone does not have the hydrogen attached to the carbonyl group. And that's how you can distinguish a ketone from an aldehyde, even though they both have the carbonyl functional group. Now here's the next one, CH3, CO2, CH3 versus CH3 and then CH2 times 3 CO2H. Go ahead and draw the Lewis structures for those two molecules. So I'm not going to completely draw it out. I'm going to expand the condensed structures. So instead of writing C with 3 hydrogens, I'm going to leave it as CH3. Now I'm going to expand this part. It's not going to be like this because carbon doesn't have 4 bonds. Instead, the CH3 is going to be attached to a carbon. We're going to have a carbonyl group and then an oxygen attached to a CH3. So this functional group is known as an ester. An ester has 2 oxygen atoms and it has a carbonyl group. On the right, we have a CH3, that's a methyl group, and then we have 3 methylene groups. So CH2, CH2, CH2. And then we have CO2H, which you can write as COOH. But we're going to expand that further. So we're going to have a carbonyl group and a hydroxyl group. So when you combine a carbonyl group and a hydroxyl group like that, you get a functional group called a carboxylic acid. Now that particular carboxylic acid has a total of 5 carbon atoms. A 5 carbon alkane is known as hexane. So a 5 carbon carboxylic acid is going to be called, wait, let me take that back. A 5 carbon alkane is not hexane, but pentane. Hexane has 6 carbons. So a 5 carbon carboxylic acid is going to be called pentanoic acid. So that's how you can name that particular carboxylic acid. Now, as for the ester, we have a methyl group, and then here we have a 2 carbon group with 2 oxygens, which is called ethanoate. So combined, this is called methyl ethanoate. If you want more examples on how to name esters, just type in ester nomenclature in the YouTube search bar, and you'll see some videos come up that has more examples on how to name esters. But that's how you can name this particular one. It's called methyl ethanoate. Now, here's a challenge problem. Go ahead and expand this particular structure. You don't have to worry about naming it, but go ahead and expand it. What I would do is I would start with the CH group there. So we have a carbon attached to a hydrogen, and then that carbon has 2 methyl groups attached to it. So we have one over here and then another one on top. So this CH is the CH that we see here. And then to the right, there is another CH next to it. So I'm going to put carbon with a hydrogen. So that's the CH of this group. And then attached to that is an OH, which we can put here. And then a CH3. The CH3s, or the methyl groups, they're always at the end of a structure, never in the middle. The CH groups tend to branch out, and CH2 groups tend to be in the middle of a structure. So let me give you another example. So let's say we have CH3 times 3, and then a carbon, and then a CH with a Br, and then a CH2, and then another CH2 times 2 followed by a CH3. Go ahead and expand that structure. So for this one, I'm going to start with a carbon atom. That carbon has 3 methyl groups connected to it. So here's the first one, here is the second one, and here is the third one. Next, we have a CH group. So I'm going to put a carbon and then a hydrogen. And then there's a bromine atom, which is going to be attached to this carbon because carbon likes to form 4 bonds. Next, we have a CH2 group, which tends to be in the middle. So that's a carbon with 2 hydrogen atoms. And then we have 2 more CH2 groups. Here's the first one, and here is the second one. And then we have a CH3 group at the end. So that's how you can quickly expand a structure that looks like that. So keep in mind, the methyl groups are at the end of a structure like this. The CH2 groups, they're in the middle. And the CH groups tend to branch off. They're also in the middle. But they tend to have other special elements attached to it, like a bromine or an OH group.